Good afternoon, everyone. This is part of Campus Energy 2021, where we're disappointingly delivering these presentations from our homes in London, Ontario, and Montreal, Quebec. But we're optimistic about 2021 and the prospects by the end of the year. Our presentation is entitled Western University's New Vision of District Energy to Mitigate Climate Change. My name's Evan Green. I'm the manager of energy and carbon and the facilities management group at Western University. And presenting with me today is Genevieve Lucier, principal at Equinox Engineering, our design partner for deep energy retrofit projects. Q&A will not be answered live. Please submit questions in the Q&A box, and Jen and I will get back to you offline in real life. An overview of today's agenda. We're going to look, I'll give you some context about Western University and our GHG reduction commitments. Jen will give you a description of our district energy network before the modifications, how we're transitioning to a future district energy system, some details about some of the projects underway right now, the concepts that we're using in new building design, and then I'll wrap up with a conclusion. So Western University and our GHG reduction commitments. Western University is located in London, Ontario, Canada. We're a public research university with almost 9.5 million square feet of building space across 82 buildings on our main campus. We're located about 2 hours south and west of Toronto. We have about 40,000 students on campus, 1,300 faculty, and 2,500 staff. Building uses range from teaching and research, including laboratories, medical and dental clinics, some substantial student residences, academic offices, and all the way to some student services and an athletic center, including a pool and an ice rink. So Western University's GHG reduction commitments. As a broader public sector institution, Western's GHG goals are set out by our provincial government. The goalposts have changed recently, but we have now, the province of Ontario has signed on to the Paris Agreement, which makes our goals to reach 30% below 2005 levels by 2030 and 80% below 2005 levels by 2050. So for Western, that means we need to get below 30,000 tons of GHG emissions by 2030 from what should be our peak in 2019 of about 54,000 tons. So the dashed green line on this graph shows the path of annual reductions that would get us to our goal. The actual path that we're going to experience to get there is going to look different. Some of the projects that we've implemented with Equinox are helping, and they're reducing our GHG emissions, but really it's going to be a shallower curve. Incrementally, we're going to reduce emissions year by year with our building level changes, and then we're going to need some system level changes that really help us drop more significantly. I'm going to pass it over to Jen to get into a description of our district energy systems before the modifications.
Thank you, Evan. So we have two chilled water plants on the campus. We have the North chilled water plant and the South chilled water plant, and we have one steam plant. So all buildings are supplied by this one steam plant. So there's about more or less 50 buildings. And the South chilled water plant supplies the buildings on the south, while the North one supplies the building on the north side. So we have steam supplied at about 100 PSIG to every building. And steam is used in different ways in every building, either to produce heating water, domestic hot water, used to humidify. And the chilled water was supplied roughly at 42 Fahrenheit to every building. And both plants come online in May, and they shut down around mid-October to the beginning of November. So as I said, it was a first generation district, 100 PSIG steam distribution, and the condensate is returned to the steam plant. So hot water for heating, the domestic hot water is produced in buildings. So there's heat exchangers in every building. Steam is used for humidification, and 50 buildings in are supplied by steam. And there's a hospital as well on the campus, and it's the sole client of Western. So all the other buildings are Western owned that are supplied by the energy. So the chilled water plants were added later on, so in the 1970s, and there's a total of 11,000 tons of refrigeration installed in both plants together. So there were many issues with the district system. So aging infrastructure, of course, piping has been installed there for many years. Insulation issues, so insulation was getting used. Over time, it was falling off. Cooling towers were reaching end of useful life, and chillers are almost there as well. So we had limit in capacity in the chilled water plants. So because buildings were added over time, and we're seeing that the chillers were at max capacity in both plants. And of course, there's the cost of peak electricity demand during summer that represents 50% of the electricity bill. So we had a lot of cost in electricity on the district. And of course, high GHG emissions due to heating demand. So we're in a northern climate. So in winter, we have to heat our buildings. So a lot of steam is consumed in winter for that heating demand. With a network of over 50 buildings with aging infrastructure, the capital cost, the estimates were quite high. So that's where the transition comes into line. How do we take that existing system and bring it to the future without having too much capital cost and, of course, reducing energy and GHG emissions? So many options were considered. For example, the replacement of steel boilers by hot water boilers. So that implied replacing almost all of the piping. Some portions could be reused, but ports, of course, with high pressure steam, the diameter is smaller, so portions of pipes had to be completely removed and replaced. So capital cost was really high for that option. There was the option of installing generators to have a cogeneration plant or a cogen to produce electricity and recovering the waste heat to produce heating water. But again, because of the structure of the electricity cost, that option again required a lot of capital investment for the savings that it generated, and there were GHG emissions related to that. There was the option of heat recovery on one of the steam boiler exhausts. So that was to recover heat from the boiler stack and use that heat for multiple use in the plant and elsewhere on campus. There was the option of centralized or local heat pumps. So either converting the entire plant with heat pumps and having an external energy source such as geothermal that was looked at. Of course, geothermal was looked at and considered. And again, with all the expansion that was going on campus, there was a new chilled water plant that was planned for the expansion and the addition of new buildings. The options that were kept were the heat recovery on the boiler exhaust and centralized and local heat pumps. Local heat pumps in buildings. So the beauty of this campus is that all buildings are connected together by the chilled water network, and that network is offline in winter. But when we look at it, it's a great network to transfer energy between one building and the other. So we're going to explain that a bit later on in the presentation. But before using that network, we had to optimize it. So first of all, the chilled water plants were optimized to reduce their peak electricity demand. So it was a traditional chilled water plant with primary and secondary pumping. So all pumping was constant, and there was that how do we say that low delta T syndrome that was experienced on the campus. So to alleviate this, project was done to have variable flow pumping, and projects were done in buildings to increase the delta T in the buildings. So that generated a reduction of about 1,000 kilowatts in demand and 3.5 million kilowatt hour in savings with that pumping strategy modification. And again, a pumping station was installed between both plants to allow operating the chilled water network as one network. So we take advantage of the most efficient chiller in both plants to to determine which one works depending on the campus load. So that transition or pumping station allowed to send 1,000 tons between one plant and the other. The North Chiller plant is underway for the optimization. So the peak demand reduction is around 600 kilowatts with 1.7 million kilowatt hour of reduction. And again, we're going to look at all the chillers that are located on the campus to connect them to the chilled water network and have many satellite chillers, again, to optimize the chilled water production. We're going to use the best efficient chiller to produce the tonnage that's required. So that's the modification that we're done to optimize that chilled water network before implementing the other measures. So here we have, again, the modification that we're done. So we have here this South Chiller water plant, the North Chiller water plant, and we have here that new pumping station that allows to either pump water from the south to the north or vice versa, from the north to the south. And again, we still have our 100 PSEG steam that's going in every building, but we're using here that network as an energy network that connects the building, every building together. And we're adding in buildings some satellite chillers or some heat pumps that will recover the energy in that chilled water loop to heat every building. So basically we're sending energy in that chilled water loop to avoid replacing here the steam plant. So over time, it's going to save capital costs because we're reducing load in every building. And when every building has been done, then we're going to figure out what we do with the steam plant. So the step 2 was the conversion to low temperature heating water by adding heat pumps in buildings. So the purpose is to convert each building that's using steam to low heating temperature water, which is about 45 degrees C. So we're not exceeding that supply temperature just to maximize the efficiency of our heat pump. Of course, there are networks that are using higher temperature water, so those networks are kept as is, but usually we're able to convert about maybe 60 to 70% of the heating demand to low temperature water. So that low temperature water is produced by local heat pumps that use the chilled water network as an energy source. So how do we get that energy? Well, in winter, a measure that's often done is free cooling in ventilation systems. So we're stopping that free cooling and doing mechanical cooling. So that means that heat that's in the building, instead of being thrown out, is thrown in that energy network and is being recovered by heat pumps. So in time, we will inject heat from renewable sources into that chilled water network. So we have a heat recovery on the flue gas from one boiler. So that's a great source of heat. So when we cool those exhaust gas, well, that heat is sent into that chilled water network and it can be recovered anywhere on campus. So we're recovering, again, heat from processes, either if it's a laboratory or like a server room or something like that. And internal heat gains as well, like for a gym or an ice rink. So all that heat is recovered and sent to that chilled water network. And of course, geothermal is going to come into play in the future as well for that. And when we can, we convert steam humidifier to high pressure water systems to remove load on the steam network. And the steam is kept for backup for heating of the building. So here we have the campus, and what's interesting is to see how can energy be shared between buildings. So for example, here we have the recreation center, which is usually an exothermic building, so heat has to be removed from that building. So we send it in the chilled water network. And here, for example, we have a science building that use heat. So the heat pumps in these buildings can recover heat from the rec center and use it to heat their systems. Same thing here, we have the nursing facility, and we have other laboratories here on the network. And here, other buildings that are exothermic, for example, the student center, building and the library. So all that energy sharing is being possible because of that energy network, or the chilled water network, connecting the buildings. So here we have the district energy vision for the future. So we have our existing chilled water network. We have external sources that we can connect that. So for example, geothermal here, a geothermal plant that we can connect in the future. We have the boiler exhaust here, and we have internal heat gains from the buildings that can all be sent to that chilled water network. So what that does is that it allows to share energy between buildings, but it allows to reduce a lot the consumption of the steam plant here without even modifying the existing infrastructure. So we're keeping all that's there, and we're reusing it in a more efficient way. So 2 existing buildings were converted that way, and it allowed to reduce the 14,000 pounds of steam, so about 1,000 tons of CO2 yearly. So the flue gas recovery system that was installed here will be able to reduce the steam consumption by 45 million pounds of steam and about 3,000 tons of GHG. Currently, we have 2 buildings that are being converted, and the projected results are to save about 19 million pounds of steam, which represent 1,300 tons of CO2. And we have a new research building that's being added on the campus, and it's expected where the energy recovery measures are expected to avoid about 10 million pounds of steam on the network and 700 tons. And also, there's a building being planned currently that is aiming 0 carbon and will be equipped with a geothermal ground source heat loop. So here we have example of projects being done in existing buildings. So we have a research laboratory that's being converted. So that project will save about 450 kilowatts of peak demand and 13,000 million pounds of steam. And it's currently consuming 19,000 pounds and about peak demands of 800 kilowatts. So these measures are going to reduce by 68% the electricity consumption and about 75% of steam reduction. And all systems are done differently in different buildings. And here we have the rec center here. So we have 6 gymnasium, a fitness center, a squash courts, a swimming pool, and a lot of AHUs. So here again, we're installing local heat pumps to produce not chilled water, but heating water. So that represents about 8.9 pounds of steam that the building is currently consuming, and we're going to reduce it by 6.5 million steam per year. So it's about 74% reduction. And we're going to reduce the CO2 emission by 480 tons. So that's about a 60% reduction. So the project we're implementing will probably reduce by more or less 1,280 tons, which is about 10% of the goal. So we still have a lot of projects to do, and still a lot of GHG emissions to reduce to reach the 2030 goal. So a lot of buildings will have to undergo this deep energy retrofit program. And like Kevin said at the beginning, we'll have to look for an external source to connect to that energy network to reduce even furthermore the steam demand. So I'm going to pass the mic back to Evan.
Thanks, Jen. So in conclusion, building level deep energy retrofit projects provide real GHG reductions. But I think everything we've identified in this presentation gets us about halfway to our 2030 goal. So system solutions are going to be necessary. It's important to maximize the utility of existing infrastructure as much as possible, which we're trying to do with our energy loop. New space must be 0 carbon to be able to meet our long-term goals, and alternative and renewable energy sources will be required to get us there. So here's our contact information, and we just want to thank everyone for listening in. We look forward to your questions.